Well, hello there, everybody. We are about to start a brand new chapter. All right, we're going to start off section 3.1 called Exponential Functions. So we're finally stepping out of the same old stuff that we've kind of been working on for the last, the entire school year at this point, and get into something a little bit different. So, first of all, exponential functions. What you can tell about what they are is any sort of function that has an exponent in the a variable in the exponent. All right, we'll see a couple of examples of what would actually look like an exponential function in a second. But as we kind of just scroll down here and take a look, we always talk about, hey, what's a real life situation? When would this be used in life? Exponential functions are actually pretty common. Right? When you talk about population growth, epidemics like COVID, that was a big one, of course. Anything that's a rapid increase or decrease, that would be considered exponential. All right. So we kind of look at this nice little cartoon. Everybody always likes to say, I'm never going to use this in real life. And then, bam, 2020 happened. And we see these exponential graphs and everything like this all over the place. So, I guess it turns out sometimes math is comes around to be useful, huh? But, anyways, let's go ahead and talk about the nitty gritty of all of this good stuff here. So, exponential function, as we mentioned, as you look here, it says f of x or y is equal to b to the x power. All right, where b is just some constant number. It's got to be positive and it cannot be equal to 1. That's what it says inside this little parentheses over here. All right, it's got to be greater than 0, but also can't be 1. And then x, being the variable, being in our exponent, can be anything. So just kind of looking down here in the bottom half, I have some examples of exponential functions. All the ones along the top row are all considered exponential. The base number is a positive number, and it's not equal to 1. And within the exponent, you see that there's an x showing up there. All right, in the bottom half, there's a bunch of things that are not exponential functions. Now, this one is raised up. Oh boy. See, it even happens here. This one's raised a lot of questions right there. Like, how come that doesn't work? Well, 1 to the x power, if you think about it, no matter what you put in for x, 1 to the second, 1 to the third, 1 to the fourth, yada, yada, it's always going to equal 1. All right, 1 to any power always equals 1. So it doesn't really change. That's what makes it not exponential. So as we get into our actual examples that I'm going to ask you to follow along with me, we see that we have an exponential function. It's got that x in the exponent. So 42.2 times 1.56 to the x power is the average amount spent in dollars at a shopping mall after X hours. All right, that's going to be important. What is the average amount spent to the nearest dollar? All right, so that's telling us how our answer should look after 4 hours. So right there, if X represents hours and it says 4 hours, we know that in this problem, our X value is 4. Now, of course, that's not our answer, right? That's just what we're taking and plugging into the equation in place of the X. So if X is 4, that means we're finding what F of 4 is. So it's 42.2 times 1.56 to the fourth power. Now, if you are using your graphing calculator, a red calculator, something like that, you could just type it in exactly as is. If you are trying to use your phone calculator or something, let's kind of take a step back here. What this equation says is 42.2 multiplied by 1.56 to the fourth power. That means 1.56 is getting multiplied 4 times. So if I'll just kind of do it along here. I'm going to multiply 1.56 to the fourth power, okay, or multiply it by itself 4 times. If you do that, it comes out to about 42.2 multiplied by 5.922, whoa, and a bunch of other stuff. Then you multiply that number by 42.2, we would get about 249.926 going on forever like that. All right, so I really wanted to kind of make sure that we understood what that's actually saying. Now, going back to the question itself, it does say what is the average amount to the nearest dollar. So we're rounding it to the nearest whole number. So the nearest whole number, of course, would just be 250. And that looks terrible. Whatever. All right, so the checkpoint that's underneath here, we're actually going to do that together in class. All right, we're going to practice all of this after you've done these notes. So hang tight with that one. Now, this next piece, all right, this is all about exponential functions and how their graphs are going to look. All right, we see on this graph over here, there's four different types of exponential functions that you can see based on just by changing the base number, how different the graph ends up looking. All right, but a couple characteristics. If we're just looking at b to the x power, meaning there's just one number to the x power, there's nothing else added in there. If that's true, then we have the domain goes from negative infinity to positive infinity, but the range would only go from 0 and up, so 0 to infinity. All right, it passes through that point 0, 1, because anything to the 0 power always equals 1. All right, and then there's no x-intercept also, just with these regular old functions. All right, if we see that the base number b is greater than 1, then the graph is increasing from left to right. So we're talking about, if you look at this graph, the green one and the black one, those both have a base that is a number bigger than 1. So those are increasing from left to right. But if it's less than 1, all right, but still greater than 0, because it's got to still be positive, like the blue one or this purplish colored one, 1/2, 3/4, then it's decreasing, right? It's going down. Okay, so as we move all the way towards the end here, it says that the graph approaches but never touches the x-axis. So that is called a horizontal asymptote. All right, so which is an imaginary line that the graph is never going to cross. So the next few examples that we're going to look at are all going to be about graphs. So a lot of times when we've graphed a function, we've made a table, and we usually go from -3 all the way to +3. All right, now once again, using your graphing calculator right here would really be helpful. All right, remember, you can type this into there's your f of x, so just type that into your y equals. Make sure that you're typing 2 to the x power, not 2x. But each of these, we would just find the f of x or the y by taking each of these x values and plugging it in. Okay, so 2 to the -3rd, that would come out to about 0.125 if you look at your table, but it's also 1/8. All right, 2 to the -2 power is 0.25, which is 1/4. Then we continue on here. We have 0.5, then we get a 1, and then now it's a little bit easier once the whole number or the positive numbers get thrown in. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. And it would continue on that way. So as we go to graph these and just kind of do our best to estimate it, at -3, we go to about 0.125. It's going to be really tough to draw that, especially in the tiny paper I gave you. All right, -2, about 0.25, about a quarter of the way. I can't really do it very well on this stupid computer I have. All right, then we have 0, 1. Then we have 1, 2. Then we have 2, 4, 3, 8. And then you notice these numbers start to really increase pretty quick. And then if you look at the other side, the numbers are going to continue to get smaller, but they never cross that x-axis. So our domain goes from -infinity to positive infinity because it's going to go on forever both ways. Our range, though, if we look at this, and we'll have to investigate a little bit more in class. But if we look at this side of our table on the y side, the numbers on the top part keep getting smaller and smaller, but they never actually get to 0. All right, the calculator is eventually just going to round it off, but if we had a calculator gave us 100 digits, eventually it'd be 0.00001 or something weird. So our range is going to be from 0 to infinity, but we need the parentheses because it doesn't actually hit that 0 number. All right, this next part, the HA, that stands for the horizontal asymptote. So we're going to say that our horizontal asymptote, I'm going to use this green marker to show this is an imaginary line that the graph is going to get really close to, but it never actually crosses it. And that's going to be right at 0 along the y-axis, along the x-axis. So the equation of that line is y equals 0. So we're going to go ahead and we'll do this part in class. And so now example 3 that we're looking at here, now it's a little bit different because the base number is a fraction. But it's not really going to change anything that we do. It's just the numbers are going to show up a little bit different. Okay, actually, well, if I go back to this really quick, because this graph is increasing, we are going to say, even though the question didn't ask us, but I always got to do extra. All right, we're going to say that that's exponential growth, right, because the graph is getting bigger. Now, as we move on to this example 3 that we're looking at, now the number's smaller, right? That 1/2. So this is going to be exponential decay. Okay, so as we start to throw these numbers in, once again, using your graphing calculator could be really helpful. Take 1/2 to the -3 power. That's actually going to come out to a +8. When you do it to -2 power, that comes out to a 4, 2, 1, 0.5, 0.25, 0.125. All right, we got those all from our graphing calculator or by just plugging each number in for x individually. But as we plot all of our points, we have -3 and 8. We have -2 and 4, -1 and 2, 0, 1. And then now is where it becomes difficult to graph because the numbers get really small. But as we connect the points together, we see that it does show that exponential decay pattern. All right, it's going downward as we go left to right. So the line that it gets really close to, that asymptote, is going to be right here in purple. Once again, right along the x-axis. All right, so our domain is not going to change. It's the same thing as the last one, -infinity to infinity. Our range goes from 0 all the way up to infinity. Hello. And then our horizontal asymptote's the same thing as before. It's y equals 0. So the tough thing about the horizontal asymptote is just looking to see where the graph looks like it's kind of stopping. All right, so checkpoint 3 will do that together as well. All right, now this next piece of this is all about transformations. And when we start throwing extra numbers or negative signs and stuff like that into the rest of the equation and the rest of the function, then it's going to just shift our graph a little bit and kind of change the way it looks. So example 4 is going to kind of show this. It says use the graph of 3 to the x power, which we kind of we'll look at in the checkpoint, to obtain the graph of 3 to the x plus 1. All right, now that x plus 1 that's up there, that's the thing that we're trying to really see what's going to change, okay? So as I go back over here, if we see there's that plus 1 in the parenthesis, in the exponent, that looks a lot like this, where we have our function, but then it's adding a number in the exponent. So what that tells us is it shifts that whole graph to the left however many units of that number that was shown there. So as we look up here, it says x plus 1. That's a transformation that is moving it to the left one space. As we continue to make our graph, all right, we can still use our graphing calculator to help us out right here. So this is going to come out to 0.111 when we plug in. All right, so we've typed in, I think my audio cut out there for a second. We've typed in into our graphing calculator this function, 3 to the x plus 1 power. If your calculator doesn't make that really fancy exponent, it would be typed in like this, 3 to the, and then you put x plus 1 in parentheses to make sure that it all goes up in the exponent part. Okay, so now as we continue on here, 0.333. All right, we plug in the next one, that's just going to come out to a 1. Plug in the next piece, that's 3, 9, 27, and then it goes all the way to 81. Now, obviously, we're not going to be able to graph all that, but we can graph as much as we can. So negative 3.111, negative 2 and 0.333, negative 1, 1, 0 and 3, 1 and 9, and look at that. That's about all we could do. All right, that wasn't the best graph, but who cares? So once again, looking for where would our asymptote be? It's going to be right along this x-axis again because the graph only shifted to the left. So that y equals 0 is still going to stay the same because it didn't move up or down. All right, our domain will still be the same thing, as will our range. Now, lastly, all right, the last one that we'll do on this video is when we see a function like this. All right, now we see the number, that minus 3, is outside of the exponent. All right, we have 2 to the x, and then minus 3 comes after it. So that one's going to be a vertical shift. Okay, that means it's going to actually shift down 3 spaces. All right, so as I go back over here, we see that that shows up right in that second spot. It's going to shift downward C units. All right, whatever that number is. So it's going to shift down 3 spaces. So let's go ahead. We have 2 to the x power minus 3. If we go ahead and fill in our table, all right, my graphing calculator is not friendly to me right now. Give me a second here, everybody. I apologize. So we have 2 to the power of negative 3, and then minus 3 from that, negative 2.875. Okay. And then we have negative 2.75 for the next value. Then we get negative 2.5. And then it continues on from here, negative 2. Right? 2 to the first power is 2. Minus 3 makes a negative 1. 2 to the second power is 4. That gives us a 1. And lastly, a 5. All right, so where this one's going to be a little bit different to look at, we have negative 3 and then negative 2.875, which means it's not quite all the way down to negative 3 on the y-axis. All right, then we have negative 2 and negative 2.75 right about in the same spot. All right, negative 1 and negative 2.5 is tough to tell. 0 and negative 2, now we get the whole numbers. So 1 and negative 1, 2 and 1, 3 and 5. And what's going to happen here is Based on those tiny little decimal numbers that we saw, it levels off right around at that -2 point something something. It keeps getting really close to that -3 on our y-axis, but it never actually crosses it, never passes that -3. So our horizontal asymptote is now at -3. All the other ones, it was at 0, but moved down 3, so it's at -3. But the rest of this stuff did not change. All right, so hopefully you were able to get most of that. We're going to work on it all together in class, all the checkpoint extra examples, and I will see you the next time.